Hello everyone, my name is Mohsen Nazemi. I got my PhD in transportation engineering from ETH Zurich. Currently, I'm a postdoc at Toronto Metropolitan University at the Laboratory of Innovations in Transportation. Today, I'm going to talk about my postdoc research and more specifically, the challenges that I faced and I had to overcome to be able to conduct my research. My research since 2016 has been at the intersection of transportation engineering, psychophysiology, and human behavior. I have been using virtual reality as the main mode of research and research method because it makes impossible possible for me. This is what I did in my PhD research. I was studying cycling safety. I was using a virtual reality bicycle simulator combined with a physiological sensor. And as you can see in the illustration on the right, I used to invite participants to come to the lab. They were sitting on a bicycle. The bicycle was fixed on a bicycle stand. We had designed different cycling environments in the virtual reality. They were going through them. We were observing their behavior, asking for their preferences. And at the same time, we had one sensor connected to their hand, which was collecting their stress level online. So we could understand which cycling infrastructure is more stressful actually for them. About my postdoc research, we want to develop an innovative approach that uses highly realistic virtual experience to understand and model pedestrian behavior. It's an international collaboration between Newcastle University in the UK and Toronto Metropolitan University in Canada. It's funded by Economic and Social Research Council UK. We know that autonomous vehicles are coming to our roads. However, one big difference is that there is no driver inside them. So pedestrians will be having difficulty communicating and negotiating the road with them. There is no eye contact, for instance, between the pedestrian and the driver because, again, there is no driver. So the question for us was that, does pedestrian behavior change in the presence of autonomous vehicles? For example, if they want to cross a street at an intersection which is not signalized, it's uncontrolled, would they have difficulty negotiating the road? So for the research method, we again use virtual reality and combined with galvanic skin response GSR sensor to measure the stress level. This is exactly the same sensor that Joe mentioned at the introduction of this session. We selected two locations, one in Toronto and one in Newcastle. We simulated them in the virtual environment. And for the case of Toronto, we selected the Union Station. We designed an experiment task for the participant. They are initially located on the sidewalk, as you can see on the left illustration. They have to walk to the yellow tactile pavement in front of them, find a safe and suitable moment to cross the street. As you can see in the figure, they need quite a large space to conduct this research. So this is different from the PhD where they were stationary sitting on a bicycle. Now the participants have to move. And this is quite large, 8 meters to 2.5. So we more or less needed 10 by 10 meter space to conduct this research. The virtual reality equipment comes originally with two base stations. These two base stations are usually installed at the corner of the room, and they track the movement of the head-mounted display. That's how you are able to see things inside VR. However, we needed a 10 by 10 meter play area to conduct our experiment. So this is the top view of the room, for example, 5 by 5. And then we said, okay, we add two more base stations and we expand this play area to 10 meter by 10 meters. However, we also had to extend the cables that were connected to the head-mounted display to just conduct the experiment again. And when we did that, we realized that, okay, there are some serious issues. For example, we had tangling issues several times happening in the middle of the experiment. The participant had to be careful with the wires while wearing the goggle, which is very hard, of course. Here, me as the researcher, I was taking care of the wires. And in several times, I had difficulty, as you can see. Participants were supposed to cross this street several times. So in the second round, for example, I tripped on the wires. At the end of this pilot session, we realized that, okay, this is not a safe setup for us to conduct the experiment. We have to think of a solution. That's why we designed this ceiling pulley system composed of a flexible curtain track rollers, ceiling brackets, and zip ties. We were not allowed to drill any holes in the ceiling, so that was one of the limitations for us. As you can see on the right side, I was quite easily and freely moving along the room while wearing the head-mounted display. And this was working nicely. So we said, okay, now we can go to the next participant. But other issues arose. And in a minute, you will see. This is the second pilot participant again, one of our colleagues. While he was making this turn, because of having loose connections to the ceiling, almost the whole ceiling pulley system fell down. Thankfully, he didn't sue us because he was a friend. In another issue with the third pilot participant, actually, while he didn't completely make the turn, as you can see, and then the wires dragged his head backward. So again, we had to fix and correct all these small issues. And in the final version of our setup, we managed to have two setups next to each other just to speed up the data collection process. It was working very satisfactorily at the end, and we were able to conduct the research. Here is an example of one of the main participants. She is walking freely in the lab. The white box on the left is showing you the output of that stress sensor that I mentioned to you. It shows you when the participant is completing the task in VR, when the stress happens, and which locations are more stressful, for example. This is the output for one of the participants for one of the sessions again, the output of that stress sensor. After some post-processing and signal processing, we can identify the stressful locations, we can identify the amplitude of the stress, and we can identify if, for example, pedestrians are facing more stress when they are dealing with autonomous vehicles. Eventually, we managed to complete the experiment with 51 pilot participants, 113 main participants, and in total 164 participants. This hectic data collection took more than 2 years to complete. And of course, we had to observe all the COVID-19 safety protocols. We distributed more than 7,000 Amazon gift cards for this whole experiment. This study actually involved one of the most complicated VR data collection processes. We initially considered using wireless headsets, but we had to make a compromise on quality, and this was definitely not desired for us. We developed a ceiling pulley system tailored for ambulatory VR setups that can be used for any other study, including walking pedestrians. The resulting dataset stands among the world's largest and most reliable datasets featuring ambulatory participants and incorporating both VR and physiological data, which will be published online soon for free access. And please stay tuned for our forthcoming manuscripts, quantifying pedestrian stress level during the street crossings in the presence of AVs. Thank you very much for your attention.